Welcome to the podcast. Today, we're going to take a deep dive into the world of time series forecasting. And if you've ever wanted to predict the future, at least when it comes to data, this is the episode for you. Time series forecasting is all about using historical data to make informed predictions about what might happen next. Whether you're trying to forecast stock prices, predict future sales, or even estimate how many customers will visit your website, time series forecasting is a powerful tool that can help guide your decision making. When we talk about time series, we're essentially referring to data that's collected at regular intervals over time. Think about things like daily temperature readings, monthly sales figures, or even hourly website traffic. The key feature here is that the data points are dependent on time, and the order in which they're observed matters a lot. We're not just looking at isolated numbers, we're looking at how those numbers evolve, change, and interact over time. So today, we'll walk through various forecasting techniques. Some are simple, some are more complex, and by the end of the episode, you'll have a good understanding of methods like Arima, Sarima, Sarimax, and even Facebook's profit model. And of course, we'll start with the basics and work our way up to more advanced methods. So let's jump in. We're going to start with naive forecasting. And as the name suggests, this is the most straightforward forecasting technique out there. In naive forecasting, you assume that the value in the next period will be the same as the value in the most recent period. For example, if you're forecasting tomorrow's weather and today's temperature is 75 degrees Fahrenheit, your naive forecast for tomorrow would also be 75 degrees Fahrenheit. Now, you might be thinking, that's way too simple to be useful, and you'd be right in many cases. But naive forecasting has its moments. It can be surprisingly effective when you're working with data that doesn't change much over time, or when you're making very short-term predictions. For instance, if you're managing stock levels in a store and you sold 100 units of a product yesterday, forecasting that you'll sell another 100 units today might not be such a bad idea if demand is stable. However, the biggest limitation of naive forecasting is that it doesn't account for trends, seasonality, or any complex patterns in the data. If your data has long-term growth or seasonal peaks, like higher sales in December due to the holiday season, naive forecasting will miss those dynamics entirely. That's why it often serves as a baseline forecast, a simple starting point to compare against more sophisticated methods. Next up is moving averages, a step above naive forecasting. Moving averages smooth out random fluctuations in the data by averaging a fixed number of previous observations. For instance, if you're forecasting sales, you might take the average of the last 3 months to predict next month's sales. The idea is simple. By averaging several data points, you reduce the impact of any one point's randomness or noise, which can help reveal the underlying trend. There are two main types of moving averages: simple moving average, SMA, and weighted moving average, WMA. The simple moving average gives equal weight to all observations, while the weighted moving average gives more importance to recent data points. For example, if you're tracking website traffic and you've seen a spike in the past few days, a weighted moving average would give more importance to those recent days, capturing the potential upward trend better than a simple moving average. However, moving averages struggle with data that has trends or seasonality. They can lag behind trends because they essentially flatten the data, making it harder to predict large changes. We will get back to the podcast in just a second. This is just a note from me that if you want to learn how to get hands-on with data, you can find courses on Python, Apache Spark, and more at cody.co.uk. Building on the idea of moving averages, we have exponential smoothing. This technique gives exponentially more weight to the most recent observations, which means it reacts more quickly to changes in the data. The rationale here is that the most recent data points are more relevant for predicting the future than older data points. There are different variations of exponential smoothing. The simplest one, called simple exponential smoothing, SES, works well when the data doesn't have any clear trend or seasonality. It's ideal for short-term forecasting when you expect the data to fluctuate around a stable average. But what if there's a trend in your data? That's where more advanced models like Holt's linear trend method come into play. This method extends simple exponential smoothing by adding another component that accounts for trends. It's great for data that has a clear upward or downward trend, but no seasonality. For example, if you're tracking the revenue of a growing startup and revenue has been increasing steadily month after month, Holt's method would capture that trend and use it to project future revenue. However, it still doesn't account for seasonal patterns. So if your data has both trends and seasonality, we'll need something even more powerful. Enter the Holt-Winters seasonal model, a variation of exponential smoothing that handles both trends and seasonality. This model is a workhorse when it comes to time series forecasting. It not only smooths the data and accounts for trends, but also incorporates a seasonal component that allows it to capture recurring patterns. This is perfect for data that has predictable seasonal peaks and valleys. Think about retail sales that spike during the holiday season or electricity usage that peaks in the summer and winter. The Holt-Winters model can handle these types of fluctuations and give you a more accurate forecast. What makes Holt-Winters so powerful is that it adjusts dynamically over time. If your seasonal patterns start to shift, say your sales peak starts to happen earlier or later in the year, the model will adapt to those changes. It's one of the most widely used forecasting models, especially in industries like retail, energy, and finance. Now let's move on to a more advanced model, Arima, which stands for Autoregressive Integrated Moving Average. Arima is one of the most commonly used time series forecasting techniques, and for good reason. It's incredibly flexible and can handle a wide variety of time series data, especially when your data has a trend but no clear seasonality. Arima combines three concepts: autoregression, which is the AR in Arima; differencing, which is the I in Arima and stands for integrated; and moving averages, which are the MA in Arima. Let's break that down. Autoregression means that your forecast is based on previous values of the time series. For example, if you're forecasting next month's sales, Arima will look at past month's sales data to inform the prediction. Differencing is used to make the data stationary, meaning it removes trends or seasonality. In other words, it transforms the data in such a way that its statistical properties stay consistent over time. Moving average smooths out noise by taking into account past forecast errors to make better predictions. One of the reasons Arima is so widely used is its ability to model a wide range of time series data by adjusting its parameters. The flexibility of Arima means that it can model data that shows signs of autocorrelation, where current values depend on past values, without the need for additional techniques to handle trends or volatility. But Arima does have its limitations. It can struggle with datasets that have complex seasonal patterns. So if your data has clear, recurring seasonal cycles, Arima might not be enough on its own. That brings us to Sarima, which stands for Seasonal Arima. It's essentially an extension of Arima that adds a seasonal component, making it much better suited for data with both trends and seasonal patterns. In Sarima, in addition to the regular autoregressive and moving average terms, there are seasonal versions of these terms that capture the repeating cycles in the data. So if you're forecasting something like monthly sales, which tend to spike during the holiday season, Sarima will help you account for that seasonality in your predictions. Sarima is extremely powerful when you're dealing with time series data that shows regular, periodic fluctuations. But like Arima, it can be a bit challenging to set up and tune correctly because there are so many parameters to consider: seasonal and non-seasonal components, order of differencing, and lag terms. Now let's take it one step further and talk about Sarimax, which stands for Seasonal Arima with exogenous variables. Sarimax is basically Sarima with a twist. It allows you to incorporate additional information or external variables into your forecasting model. These external variables, called exogenous variables, are factors outside of your time series that can influence your forecast. For example, let's say you're forecasting sales for an online store, and you know that advertising spend heavily influences sales. In this case, you could use Sarimax to include advertising spend as an exogenous variable, which would improve the accuracy of your forecast by taking into account this external factor. Sarimax is particularly useful when you know that external factors play a significant role in shaping your time series. It's a way to build a more complete picture of what's driving the data rather than relying solely on past values of the time series itself. Now, let's shift gears and talk about a relatively new kid on the block, Facebook's profit model. Profit was developed by Facebook specifically for time series forecasting, especially for datasets with strong seasonal patterns and missing data. One of the things that makes Profit stand out from other forecasting models is its focus on simplicity and ease of use, while still being powerful enough to handle complex time series data. Profit is designed to be intuitive and flexible, making it accessible to users who might not be experts in time series modeling. This means that you don't need a deep understanding of the underlying math to get good results. But despite being user-friendly, Profit is still very robust and can handle a wide range of real-world problems. The key features of the Profit model are its ability to capture trends, seasonality, and holidays or events, things that other models like Arima or Holt Winters often struggle with. What's particularly interesting is how Profit handles holidays. If you're forecasting retail sales, for instance, you might know that sales always spike around Black Friday or Christmas. Profit allows you to include those events in your model explicitly, so your forecasts account for those one-off spikes that might otherwise throw off a traditional forecasting model. Let's break down how Profit works. It decomposes the time series into three main components: trend, seasonality, and holidays or events. The trend component models long-term growth or decline in the data. The seasonality component captures repeating patterns like daily, weekly, or yearly cycles. And the holidays component allows you to incorporate special events that can cause deviations from the normal trend or seasonal patterns. What sets Profit apart is its flexibility with trend changes. In many real-world datasets, trends don't stay constant. They might shift due to external factors like new market conditions, product launches, or economic changes. Profit allows for change points, which are moments when the trend can shift, and it automatically detects them. So if you're forecasting sales and notice that the introduction of a new product caused a sudden spike in sales, Profit will identify that change point and adjust its future forecasts accordingly. One of the things I love about Profit is how well it handles missing data. In many cases, time series data is messy. You might have missing observations due to data collection errors or other factors. Profit doesn't require you to have a perfectly clean dataset, which makes it a great choice for situations where data isn't complete or where anomalies are common. Another feature is that Profit is designed to work well out of the box without much need for parameter tuning. For users who are not experienced in machine learning or statistical modeling, this is a huge advantage because you can still get highly accurate forecasts without spending a lot of time tweaking the model. Now that we've covered traditional models like Arima, Sarima, Sarimax, and Profit, let's touch on machine learning approaches to time series forecasting. Over the past decade, machine learning has become a game changer in many areas, and time series forecasting is no exception. Unlike statistical models that assume linear relationships and require stationary data, machine learning models can handle nonlinear relationships and complex patterns without requiring a lot of manual pre-processing. Machine learning models like random forests, gradient boosting machines, and neural networks are increasingly being applied to time series forecasting because they can capture complex patterns that traditional models might miss. These models don't rely on assumptions like stationarity or linearity. Instead, they learn from the data itself, often performing better in cases where the data is highly complex or where there are interactions between multiple variables. One of the main benefits of using machine learning models for time series forecasting is that they can handle multiple features. For example, if you're forecasting sales, a machine learning model could consider additional factors like weather, advertising spend, economic indicators, and even customer sentiment from social media. This allows for richer forecasts that capture the interplay between various variables in ways that traditional models like Arima might not. Random forests and gradient boosting machines are popular machine learning algorithms used in time series forecasting. Unlike Arima, Sarima, or Profit, these models don't rely solely on past values of the target variable, like sales or temperature. Instead, they can incorporate exogenous variables, similar to Sarimax, but in a more flexible and data-driven way. In random forests, the model creates multiple decision trees based on random subsets of the data and then averages the results. This is powerful for time series data because it can model nonlinear relationships, capturing more complex interactions between time series values and external factors. Gradient boosting works similarly, but instead of building trees in parallel, it builds them sequentially, with each new tree trying to correct the errors made by the previous trees. This sequential nature helps gradient boosting machines to be more precise in certain cases. However, these models still have their limitations. One key issue is that while they can handle complex relationships between variables, they don't inherently account for time dependency in the same way Arima or Profit does. This means that they might miss trends or seasonality unless you engineer those features manually by adding lagged values, trend indicators, or cyclical patterns as features. Another promising machine learning approach is the use of neural networks, especially models like recurrent neural networks, RNNs, and long short-term memory, LSTM networks, which are specifically designed to handle sequential data. RNNs and LSTMs are great for time series forecasting because they maintain a memory of previous inputs, allowing them to model time dependencies more effectively. LSTMs are particularly good at capturing long-term dependencies in time series data. For example, if you're forecasting energy consumption and there's a clear seasonal pattern that repeats every year, LSTMs can recognize and model those long-term cycles. Unlike traditional models like ARIMA, LSTMS don't require the data to be stationary, and they can capture complex nonlinear relationships without needing much manual feature engineering. However, neural networks, especially LSTMs, require a lot of data to train effectively. They also need more computational power and can be harder to interpret compared to simpler models like ARIMA or even random forests. This makes them more suitable for large datasets with complex patterns, but they may not be the best choice for small datasets or cases where interpretability is crucial. Now that we've covered several different forecasting techniques, let's talk about when to use which model. One of the key challenges in time series forecasting is choosing the right model for the specific dataset and forecasting problem you're dealing with. Naive and moving averages are good if you're working with very short-term forecasts or data that doesn't change much over time. Naive or moving average methods can be surprisingly effective. They're simple to implement and don't require much tuning. Exponential smoothing and Holt Winters is suitable when your data has a clear trend or seasonality, but you're looking for something more sophisticated than a simple moving average. Exponential smoothing methods, like Holt Winters, are a great choice. These models are ideal for retail sales, electricity usage, or any other data set with regular seasonal cycles. Arima and Sarima are a good fit if your data shows signs of autocorrelation, meaning future values depend on past values, but doesn't have clear seasonality. Arima is a solid option. Sarima extends Arima to handle seasonality, making it useful for monthly or quarterly data with clear seasonal patterns, such as sales or temperature data. These models are widely used in financial and economic forecasting. Sarimax can be considered when you have external variables influencing your time series, like advertising spend, weather data, or other external factors. Sarimax is the way to go. It allows you to model those exogenous variables along with the time series itself, improving accuracy. Profit is an option if you need something that's easy to use but still powerful, especially when dealing with messy data, seasonal patterns, or holidays. Profit is a great option. It's particularly useful for business applications like forecasting website traffic, sales, or social media activity, where you may need to account for events like promotions or holidays. Machine learning is an option. When you have a complex data set with multiple interacting variables, machine learning models like random forests, gradient boosting, or LSTMs can provide the most accurate forecasts. These models are ideal for data sets where nonlinear relationships or long-term dependencies are at play, such as energy demand forecasting or predicting stock prices. So, what's the takeaway from all of this? Time series forecasting is a powerful tool, but the choice of model depends heavily on the nature of your data and the specific forecasting problem you're trying to solve. Simpler models like moving averages or exponential smoothing are great for short-term forecasts or when your data doesn't have complicated trends or seasonality. On the other hand, if your data has strong seasonal patterns or external influences, models like Sarimax or Profit might be a better fit. For those working with large, complex data sets, especially ones with multiple variables influencing the time series, machine learning models like random forests, GBMs, or neural networks can offer the best accuracy, although they require more data and computational resources. At the end of the day, it's all about experimentation. Time series forecasting isn't a one-size-fits-all solution. Often, the best approach is to try out different models, compare their performance, and choose the one that works best for your specific data and needs. Thanks for tuning in to today's episode. I hope this deep dive into time series forecasting has given you a clearer understanding of the different techniques available and when to use them. Keep experimenting with different models and, as always, happy forecasting.